myself Shivi and Dr. Kiran Yadav. In this session, I will discuss about Heisenberg uncertainty principle. The Heisenberg uncertainty principle was given in 1926. Heisenberg thought about measuring simultaneously the position and momentum of an electron, and he found that the measurement of both with precision is impossible. In fact, the measurement process perturbs the system. So, the Heisenberg basically says that we cannot simultaneously measure position and momentum of a particle. Measuring the position of a very small particle, such as an electron, requires the use of short wavelength light. That means high frequency, high momentum light. High frequency light would alter the electron's momentum. Use low frequency light and the position of the electron is not well determined. The Heisenberg uncertainty principle has several forms. We denote the uncertainty in momentum, for example, by delta P. In one dimension, we can write the equation as delta P x delta x is nearly equal to h. If q denotes the three-dimensional position coordinate, then del p by del q is greater than h upon 4 pi. This is the Heisenberg principle. Since measurement p is equals to mu, where u is velocity, the Heisenberg expression can also be written as del u into del q is greater than equal to h upon 4 pi m. Here we have written m del u in place of del p. This equation tells us that the product of the uncertainties in velocity and position decreases as the mass of the particle increases. Ignoring history, Heisenberg tells us that as the mass of a particle increases, we move towards a deterministic description, that is the Newtonian description. Now, Heisenberg and Spectroscopy. The Heisenberg expression can be recast in terms of energy and time also. So, in terms of energy and time, the expression can be written as del E into del T is greater than equal to h upon 4 pi. It relates in real life to widths of spectral lines. In electronic emission spectra, del T can be small, short lifetime in the excited state. This means that del E will be large. The transition energy covers a range of values. The observed spectral line is broadened. De Broglie electrons and waves. Einstein's theory of relativity tells us that the energy of a particle having a momentum p and rest mass m is given by E is equals to p square c square plus m square c4. In our interest lies in photons, which have zero rest mass. Then energy of photon is equals to p into c. That means p lambda v. Using the familiar expression from Planck, which was E is equals to h nu, we get for photons lambda is equals to h upon p. De Broglie suggested that this last expression could apply to beams of particles with a finite rest mass m and velocity u. So the momentum comes out to be p is equals to mu. So now let's discuss about de Broglie and diffraction. For finite rest mass particles, de Broglie gives us lambda is equals to hp, and in place of p we can write mu, so it can be written as h divided by mu. This expression does have meaning in our physical world. Wave properties of subatomic particles and light molecules have been demonstrated though. For example, a variety of diffraction experiments. So this was about Heisenberg uncertainty principle and de Broglie hypothesis. So that's all for this session. We will continue our discussion in the next session. Thank you.